Dear students, so in the previous class, we had derived an equation for the forced oscillation, that is the amplitude for the forced oscillation. And there we had primarily the three factors, that is the three driving force you can say. One was the natural frequency, and the natural frequency we had called as omega naught. And another was the force frequency, which is the force frequency we had called as omega. And third was the damping coefficient, that the medium in which it is vibrating. Then in all these conditions, under that conditions, if the object is vibrating, then we have derived the equation for the amplitude. That is, if the omega is going to vary, or omega naught is going to vary, or damping coefficient is going to vary, then how the amplitude of the oscillations is going to vary. That equation we had derived, we have not done the analysis. So today in this class we are going to do in detail analysis of the amplitude of the forced oscillation, and then after seeing that we'll see what will be the condition of the resonance. So what we should do, that we should get the maximum amplitude. Condition of the resonance is nothing, it is a function at which we can get the maximum value of the amplitude, right? So this is what we are going to look into in today's class. And therefore, at the concluding, I will take up one of the engineering applications, and then I will tell you how the resonance have got the engineering applications, apart from some of the magical applications, as I had told you, the Tansen used to break the glass ceiling while he was singing. So that we are going to look into. So let's start with. So therefore, now let's start with the condition of the resonance. So what is the condition of the resonance? One of the most important phenomena of the force oscillation is the resonance, where the amplitude of the vibration increases to huge magnitude depending upon the presence of the damping in the structure or the medium. It happens once the forcing frequency matches with the one of the fundamental frequency of the structure. So let us try to understand what I mean with this. So what I'm telling you, let us suppose here we have got a swing, or let us suppose we have got a pendulum, and this pendulum is oscillating with a frequency, and let us suppose that frequency is your omega naught. So it is oscillating like this, and let us suppose the frequency with which it is oscillating is your omega naught. So this we are calling as your natural frequency. Now let us suppose I'm going to apply a force on this, right? We have applied a force on this, and that is also your SHM type of the force we are applying, which we have called as A cos omega t, where omega is your applied frequency. So omega is your applied frequency that you are putting on this mass, that is on the bob of this pendulum. Then what is going to happen, depending upon the relation between this your omega and your omega naught, omega and omega naught, this value of the amplitude is going to vary. So this amplitude may be coming up to here, or again it may be going up to here. So here the amplitude is going to vary. We are going to say whenever this value of the omega and omega naught are going to be equal, then what is going to happen? So that will be the condition of the resonance, and this is what we want to understand from the equations that we have already derived in the previous class. So here I am going to do in the two parts. Equation that we had derived in the our previous equation for the amplitude of the force oscillation is A equal to F, and F was, as you may be remembering, A by M. What was the F? F was equal to A by M, where A was your applied amplitude and M is the mass on which you are going to apply. So F was nothing, F was equal to your, if you remember, you can go back and you can see A by M, where A was the amplitude that you had applied, that is the force amplitude you had applied on the mass, right? So F equal to A equal to F by omega naught minus omega whole square plus 4 gamma square omega square. Now you see here you have the three factors. One is your omega naught. Omega naught is your natural frequency, just I have explained you. Omega is the driving frequency, that is your the external frequency that you are going to put, and gamma is the medium in which it is going to oscillate. Gamma is equal to 2 gamma we had taken, B by M is equal to 2 gamma we had taken. So this is your nothing, this is your of the characteristics of the medium. Now here we are going to deal this equation in the two part. First we are taking the undamped oscillations. As you see here, case 1 is your undamped oscillations. When it is going to be undamped, if the value of the gamma is going to be 0, that is there is no damping in the medium, and that will call your undamped oscillation. So first let us see the undamped oscillation. In case of the undamped oscillation, what we'll have, so here we are seeing the value of the gamma equal to 0, and then value of the amplitude A that we are getting is equal to f upon omega minus omega naught square minus omega square. This is the amplitude of the oscillations. Naturally, you can see over here that here we have the two factors we are getting, omega naught and omega, right? So as this total value is going to, this value that is denominator is going to decrease, your A is going to increase, right? How denominator will decrease? If the value of the omega is going to increase, so slowly let us suppose I'm driving force, that is driving frequency, slowly we are increasing. So then this denominator is going to decrease, denominator will go on decreasing, and the omega A is going to increase, right? Now let us suppose after some time this omega naught become equal to omega, that is the natural frequency with which it was vibrating, and that is equal to the external frequency that we have given. These two are going to matches, and moment these two are going to match, this value is going to be 0. This denominator is going to be 0. So anything to be divided by denominator 0 is going to be infinity. So what I am saying, the amplitude here practically is going, mathematically at least we can say, is going to be take the infinite value. That is, amplitude is going to take the maximum value. Now if I am going to further increase the value of your omega, right, then this will become negative, this value will become negative. That is, in that case, the amplitude that is taking place, the vibration that is taking place, it is going to change the phase, right? So let us try to understand with one of the example over here. So here what I have done, here I have taken the ping ball with which you must have played, that is, here you have the rubber type of the string, and here you have a mass which is also of the rubber type, right, and that you have tied in your finger, right? Now here you have started oscillating this ping ball with your finger. So let us suppose initially you are going to give very small frequency f, the value of the f, that is omega. Over here we can say the value of the omega is very small. Then this is the maximum amplitude that you can see here, it is going up to here, similarly it is coming over here. So this is the value of the 2x, that is x it is going up, x it is going down. So this is the value of your x. Now what you are going to do, slowly you are going to increase the value of omega. Natural frequency of course you cannot change. So what you can change, you can change the driving frequency, that is omega. So omega here I am going to increase. So slowly I am going to increase the value of the omega, and as you can see the value of the 2x is increasing. So here now the ping ball has come over here, and again it has come over here. So at this point what I'm saying, the value of your omega naught and omega has become equal, and at that point you are getting the maximum frequency. Now if you are going to further increase, it is going to change the phase. So that is, its vibration will get reverse. So if it was vibrating in this direction, right, then its vibration direction is, that is the phase of the is changing, and this will be coming in this direction. So I'm going to take tell you in the next slide how it is going to change the phase. So it will be changing the phase, and ultimately its total amplitude is going to decrease. So what we are finding, you can say you will be getting some type of the Gaussian curve like this. Slowly the amplitude is increasing, it will take the maximum value, and then after that it is going to decrease. So this is called the Gaussian curve. So here this is the maximum, this is the point of the maximum amplitude. So what we have done here, you have taken, this is your amplitude that we have taken, and this is the frequency that you are taking, this is your frequency you are taking, right, omega, and here this your omega has become equal to your omega naught. So omega has become equal to your omega naught. So moment these two has become equal, at that point you have got the maximum amplitude, and then again as you are going beyond this, the phase has changed, and then of course its amplitude is going to decrease. Let us see it a little more elaboration with help of the. So it is evident from the equation that as omega increases, A also increases, and it takes the maximum value when omega is equal to omega naught. That you must have understood. For the further increase of the omega, amplitude A start decreasing. The curve below explains the variation of the amplitude A with the force frequency omega, the maximum value of the amplitude when omega is equal to omega naught is called your undamped resonance. Undamped amplitude resonance, because here what we have done, the gamma we have made 0, so it is your natural frequency, right, has become equal to your force frequency without any disturbing medium, that is any resistive medium, and in that case the amplitude is getting maximum, and that is called your undamped amplitude resonance. So this is let us say what will be here phase will be equal to tan inverse from that we have already seen in the previous class, 2a omega gamma upon omega naught a, so omega naught square a minus a omega square, so a I have taken out, so this is the value of the phase we are getting, tan inverse 2 omega gamma upon omega naught square minus gamma square. Now what we are saying, we are going to get the resonance when these two values are going to be equal, so naturally this value will equal to your tan inverse infinity, so this is what we have taken. So at the resonance you are getting tan inverse infinity, and at the resonance you are getting this value of the phase is equal to pi by 2. So at the value of phase pi by 2 you are getting the resonance. Naturally if you are going to increase beyond this, you are going to get in the minus, right, and therefore its phase has got changed. The resonance occurred at a phase of pi by 2 in case of undamped oscillation, and naturally this is the oscillations that I had told you in the previous class. So previous slide. So as you are going to increase your frequency, that is the driving frequency or your force frequency omega, as you can see over here, you are slowly increasing from here. Let us suppose from 0 you are slowly increasing, right? Natural frequency will have at one point only, you cannot change the natural frequency, so slowly you are increasing and you have come near to your natural frequency. Moment you have come to the natural frequency, you can say it has increased exponentially, and of course mathematically we are saying its amplitude has got maximum value, right? This is what I have tried to show you with the diagram. I have not closed the tips. And then of course its value is decreasing exponentially. After that it is decreasing. The moment you have crossed over your omega naught, it is decreasing, but of course its phase has got reverse. So this is your undamped resonance. Now I'm going to see the second type of this, where the damping medium gamma is also there, and then with the gamma the resonance. So let us try to understand this. So this is your undamped oscillations. So the amplitude of the oscillations we have already got, omega naught square minus omega square plus 4 gamma square omega square. So this is the value of your amplitude in case of the force oscillation. Now here I am not saying that this medium is not there, is gamma is also there. If the gamma is also there, then when we are going to get the maximum amplitude, and that wherever we are going to get the maximum amplitude, that will be called as your condition of the resonance. How we can get this? So we can say the first derivative of your denominator here, the first derivative should be 0 and second derivative should be negative. Then what we can say, the amplitude value will equal to your maximum. So when we will have the maximum, if I am going to differentiate this and the first derivative of this is going to be 0 and second derivative is going to be negative, then for that value of your omega or omega naught or gamma, whatever you are getting, for that value, whatever the condition is coming, that value we will have to substitute in the equation 1, and at that point the amplitude that you will be getting will be your maximum amplitude, right? So equating the first derivative of denominator of the above equation to 0. So let us do this. So I have taken the first derivative of this. So the first derivative over here has been taken. So what we get here, the value of your omega square is equal to minus omega naught square minus 2 gamma square. So this is the value of relation that we are getting, right? So omega square equal to omega naught square minus 2 gamma square. So what do you do in this equation number 1? Here wherever you have the omega, here you have the omega, and here also you have the omega. So in the place of your omega or omega square, whatever you have, you place the value of omega naught square minus 2 gamma square. Substitute this value in equation 1, solve this, and that value will give you the condition for maximum amplitude, and we'll call that will be as a forced damped oscillations. Here I'm sorry, it should be your damped oscillations. All right. So now here what we can say, this is what I have done over here. So f, this is your equation, a equal to f upon omega naught square minus omega square whole square plus 4 gamma square omega square. This is 4 gamma square omega square. This is the value that we have got over there. Now what I'm going to do here, the value of the omega I'm going to substitute this value, and this value of the omega I'm going to substitute. So this is what I have done. I have substituted this value over here, and again I have substituted the value over here. Just I have solved this, and then I'm getting the value of the amplitude A is equal to, this is nothing, this is the value of the amplitude equal to f upon 2 gamma, right? Gamma is of, as you know, it's a damping coefficient, omega naught square minus gamma square. Omega naught square is your naturally is your natural frequency, and again gamma that you are getting is of the damping coefficient of the medium. So naturally here, this is nothing, this is your A, amplitude this is your A. So naturally here what we can say, A is inversely proportional to your gamma, because this separate term is there, so there should not be any confusion over there. A is inversely proportional to gamma. So as the value of the gamma is going to increase, right, then what is going to be its effect on the amplitude? Naturally it is your inversely proportional, right? And then what we can say, if omega naught square and gamma square is going to be equal, then naturally this value is going to be 0, and then we'll be getting the maximum value of the amplitude. And this is what I have tried to show with the following curve. So what we are saying, thus it is clear from the above equation that A equal to, the value of A that we have got is A equal to A equal to f upon 2 gamma omega naught square minus gamma square. So the amplitude is inversely proportional to the damping coefficient gamma, inversely proportional to your damping coefficient. The same can be represented with the following curve. So now here you see, here the value of the damping coefficient is large, b by 2m is equal to b by m, here we have taken is equal to omega 1 upon 2 omega naught, right? So b by 2m is the value of this, is your this value. Now what I'm going to do, slowly I'm going to decrease this value. So naturally if you are going to decrease this value, the amplitude is going to increase. So what I have done here, b by 2m is equal to, I'm taking 1 upon 4 omega naught. Here b by 2m equal to, we have taken 1 upon 2 omega naught, right? Now I have decreased to 1 upon 4 omega naught, and then I have further decreased by 1 upon 8 omega naught. As you can see, as I am decreasing the value of the damping coefficient, b by 2m is nothing, gamma, as you know, b by 2m is your gamma. So as I am going to decrease this value, amplitude is going to increase, because it is inversely proportional. As you can see from your equation, it is your inversely proportional. So here what we can see, the first curve that we are you are saying, that is it is your at a very heavy damping medium. It's a very heavy damping medium, and as we are going up, the damping medium is getting lighter, and of course the amplitude is going to increase. Let us see with one more curve. So this is what I have shown you here. If it is very heavily damped, then naturally what we are getting, if it is very heavily damped, its amplitude is smaller, right? But as the damping is being lightened, then what is happening? Its value is, the amplitude value is increasing, and when the value of the gamma is very small, and this two value is also going to equal, gamma and omega naught is going to equal, right? Then so because here gamma and omega naught relation I am taking, so ultimately we are saying gamma has become equal to your omega naught. So this value, with this value I have plotted the curve over here. So gamma has become equal to omega naught, and the value of the gamma has become very small, so it is almost undamped, and then as you can see over here, the amplitude you are getting is your maximum, and that is also called your sharpness of resonance. So my dear friends, in this way we have seen the condition of the resonance, and let us see this small animation in your daily life. So here you have, one is your swing. Swing is naturally oscillating, and let us suppose that frequency is your omega naught. and here one child is sitting over there. He is also exerting a force on that. So moment he is going to exert a force on that, so he is giving this another wave on that, that is a cos omega t, right? So if he is able to maintain the relation between the natural frequency, right, natural frequency of your swing, that is omega naught, and the force that he is applying on the swing, that is omega, if these two values are coming nearly equal, he will be getting the maximum value of the amplitude and he can enjoy maximum. Moment if he is not able to give that much, naturally he cannot get that much value of the amplitude, and naturally his enjoyment is going to die down. He will not have that type of the enjoyment over there. So in this way, so now you see your example that I had quoted you, that when Tansen used to play his musical instrument, so he has the art and he was knowing what is the natural frequency of the glass ceiling. You must be knowing that each and everything is oscillating, right? You don't have any object in the world which is not oscillating. Everything is vibrating. And with the frequency which that it is vibrating is called the natural frequency, right? So when he used to play his musical instrument, he has the art that he was able to produce the frequency with his musical instrument, which was equal to the glass ceiling. And of course, in that case, the glass used to break with used to oscillate with the amplitude, and it was going to such an amplitude that it was not able to return back. And of course, it was not able to sustain that type of the amplitude, and it was breaking. Now, maybe in your childhood, you may have heard one of the phenomenon that when the army is marching on the bridge, he is not allowed to march over the bridge, right? Up to the bridge he can march, but moment he has to cross over the bridge, he is not allowed to do the marching. Marching does mean the shoulders will take up the foot together and put it down together. So that is not being allowed, because the bridge will have also a particular value of the frequency, which is called the natural frequency. But incidentally, if the soldier is marching on that, and he is going to produce a resultant wave, and that resultant wave will have a particular value of the resultant frequency, and that resultant frequency is incidentally, if it is going to match with the natural frequency of the bridge, so bridge will collapse. So in that way, this is why the soldier is not allowed to march over the bridge. So these are some of the applications. Now there are a lot of engineering applications. One of the engineering applications maybe you may have done in your 10+2 levels, where you have measured the frequency of the AC mains using sonometer. In case of the sonometer, you must be remembering that you have a wooden frame, right? And inside the wooden frame you have the air, and then you are going to give the electrical connection. So the air column in that frame will be vibrating, and when the air column is going to vibrate, and that vibration is coming to be equal to the frequency of the AC mains which you have applied in your wire in case of your sonometer. If these two are becoming equal, the wire will start oscillating with a very high amplitude, which you can see with your naked eye as well, right? And at that point you take the reading, and this is how you find out the with the mathematical calculation the frequency of AC mains, right? There are many electronic example of the force oscillations. So when you will come to the lab, I will show you, right, some of the engineering applications there, right? So by the time being, that was your force oscillation. And now in the next class I am going to take up maybe one more applications of that in terms of the Helmholtz resonator, right? And that will be your last class on your waves and oscillations. Thank you very much.